All right, today we're going to be talking about the transformations of polynomial functions. And the base functions we will be using today to demonstrate these transformations will be the x squared function and the x cubed function as we need them. So those will be the two main ones that we'll use to actually transform. Okay, so here we're going to talk about vertical shifts. And there's going to be two sides to vertical shifting up and of course shifting down. So our first transformation, which it will tell you, is y equals f of x plus c. Now here c of course is your constant, and here we will be using x squared as our base function. Now I've given an example here. You have y equals x squared plus 2. In this example here, you will be shifting the graph up and down the y-axis. So in this case, y equals x squared plus 2, you will go up 2 units along the y-axis from the origin of where your base function starts. So simply, as you can see here with the green, we've just moved it up 2 points to the 2 unit on the y-axis. Now the reverse of that would be y equals f of x minus c. So in this case, I use the same example, except we're going to go down 2 units along the y-axis here. So I have y equals x squared minus 2. So you're going to take your original base function, which was based at the origin, and you're going to shift it down 2 units on the y-axis. And there you have it, a vertical shift in both directions. All right, now we're going to talk about horizontal shifts. Now, horizontal shifts, once again, we're going to be using the base equation of x squared. Here, though, you should note that our equations, now the c is actually in the parentheses with the x. So you can see that in both equations here, that the c is now in the parentheses. This is very important to note so you don't accidentally do a vertical shift. So, another thing you need to know about these is that they are somewhat counterintuitive. For example, in our first one, we have y equals f of x plus c, with of course c being in the parentheses. I've given an example here, y equals f of x plus 3 squared. So in this case, even though it is plus 3, you're actually going to be moving on the negative side of the x-axis. So since it is horizontal, you're moving along the x-axis. So do note that when it does say plus 3 or plus c, you're actually moving along the negative part of the x-axis. So bear that in mind. So as you can see here, we have our base equation x squared, and we just shifted 3 units in the negative direction of the x-axis. All right? Here we have the reverse of that, which is y equals f of x minus c squared, in this case, our base equation. And of course, I've used 3 again in this case. Now, as you can see here, you're going to move along the positive x-axis. So this can be somewhat counterintuitive, and it's just something you have to remember. But this is how you're going to do horizontal shifting. All right, here we're going to talk about another type of transformation, and this is horizontal scaling. Now here, you're going to see that the c is still inside of the parentheses in your base equation here, but it is actually being multiplied by your variable, x, in this case. So once again, we're staying true to the x squared as your base equation. So here you're going to see that if your c, so this is where your c actually, its value actually matters. So if your c is actually greater than 1, or greater than or greater than 1, I'm sorry. If your c is actually greater than 1, then you're actually going to squeeze the graph like so, thinner than your base equation. So here, as you can see, you have y equals f of 2x squared. So you have your x squared right here, which is in the black. That's going to be your base equation, and in the blue dots is actually your example function here. So as you can see, it's actually been made a little skinnier than its base equation. So what you're doing here is you're actually compressing it in the x direction, as if 2 forces were converging from both directions of the x-axis, thus squeezing it and making it smaller than its base equation. We're going to go down here and we're also going to see this same thing, except now your c is actually greater than 0, but it's less than 1. So pretty much you've just turned it into a fraction. So as you can see here, you have y equals f of 1/2 x squared. So in this case, you're actually going to expand it out. You're actually going to stretch it out along the x-axis, as if you were pulling it from both directions of the x-axis and making it bigger. So as you can see here, this is horizontal scaling. Okay, so now we're going to talk about vertical scaling. Here you're going to see it somewhat is the reverse of horizontal scaling. So here you see our main difference is that our c actually lies outside of the equation completely, and it's actually timesing itself by the entire equation that you have. So once again, we're using x squared as our base equation. So in this case, when your c is greater than 1, you will actually make it skinnier than what you normally would. And how you're going to do that is you're actually going to put forces on it from the you're actually going to stretch it. I'm sorry. You're actually going to stretch it in this case, and when you stretch it, you're actually going to pull it up and down the y-axis. So let's say you would actually grab it from the top, and you would actually grab it from the bottom of the graph along the y-axis, and you would actually just stretch it, and you stretch it out, and you make it thinner. So that's what's going to happen when your c is greater than 1, and the reverse is going to happen when you have a c that is greater than 0 but less than 1. So here you're actually going to crush it, compress it from the y-axis. And that's really the best way to think about it. You want to think about this along the y-axis since you are dealing with vertical scaling. So what you're going to do here is as if two forces were coming from each side of the y-axis and crushing it, thus making it thicker. So as you can see, the two examples I have here, I use 2 as our factor here. And you're going to actually stretch it here and make it thinner by a factor of 2. Here we have the same thing, except you're compressing it by a factor of 2, which in this case you have y equals 1/2 times f of x squared, which is going to give you a fatter graph due to two forces crushing down on it from the y-axis. Okay, and here we're going to talk about our final transformation, which is reflections about both of our axes, the x-axis and the y-axis. So here we're going to look at reflections about our x-axis first. So here we have, to reflect around the x-axis, we have to have an equation y equals negative f of x. So you're essentially putting a negative sign in front of the entire equation. So once again, we're using our base equation of x squared. X squared is in the black here. And here you're going to have our example equation of y equals negative x squared, naturally. So here you have the x squared base equation, and the blue dots are going to be our example equation that we just read. So as you can see, it is actually reflected like a mirror across the x-axis. The x-axis is the mirror, and it has its reflection, which is the blue dots, naturally. Now this is where things can get a little trickier. Now here you have y equals f of negative x when you want to transform it reflecting about the y-axis. Now we use the x cubed equation here because the x squared equation, as you can see, is already reflected about the y-axis in its base equation. So here we're going to use x cubed, and let me add that really fast. Alright, so there we go. Added that cubed for you at the end of our green equation there. So once again, we have y equals f of negative x, the negative now being inside the parentheses with the x, thus making all your x values negative in this case. So here you see we have y equals f of negative x cubed. So in this case, what you're going to be doing is you're actually just going to be flipping the graph in a way, because you're going to flip it and reflect it about the y-axis. As you can see, your x cubed equation is in the black. So you can see that it is on one side of itself, and then you see that the green dot is actually a reflection across the y-axis. So as you can see, the top half is a reflection, and then you see the bottom half is a reflection. So you're actually reflecting about the y-axis in this case. That is going to be all of your transformations. Thank you for watching.